Hello, and thank you for joining us for today's webinar, Rguroo Tools for Teaching Proportion Inference using the Binomial Exact and the Normal Theory Methods. My name is Danny Shapiro, and I'm on the marketing team here at Hawks Learning. Our speaker today is Dr. Mori Jamshidian of California State University, Fullerton. Dr. Jamshidian is a CNSM Distinguished Professor in the Mathematics Department and serves as the graduate advisor for the Masters of Science in Statistics. His past positions include Associate Professor of Statistics at the University of Central Florida and Senior Statistician at the BMDP Statistical Software. His area of research is broadly in computational statistics, with publications in major theoretical and applied journals, such as the Journal of the American Statistical Association, Journal of the Royal Statistical Society, Biometrica, and Psychometrica. He is currently an associate editor for the Journal of Computational and Graphical Statistics, and in the past has served as associate editor for the American Statistician, Journal of Statistical Software, and Journal of Statistical Computation and Simulations. His current activities include research in statistics education and the development of statistical software for teaching statistics. We are excited to have Dr. Jamshidian here with us today to continue to further explore Rguroo. If you do have any questions during the webinar, please enter those into the Q&A box located on the panel at the top or bottom of your screen, and we will address them at the end of the talk. And on that note, I would like to hand it over to our presenter.
Thank you, Danny, and good afternoon, everyone. So I'm going to start the webinar with a quick overview of Rguroo first, just in case you're not familiar with Rguroo, and then I will get into talking about proportion inference, which is the main topic of the webinar. So let me just move to an overview of Rguroo. So generally speaking, you would just use, you could go through our website and use the login page to log into Rguroo. What I'm going to do today is I will use our development site, which has the latest developments in Rguroo, and I will point out what are new actually in the new version that's coming up. So essentially, the software, when you open it up, it involves four sections. One is data, one is plots, another one is analytics, and another is probability simulation. And within each of these sections, there are various functions. So you have data import, which is the basic and important function for importing data into the cloud. So all of the data are imported into the cloud, and you could, for example, import data with various formats, CSV, Excel, SAS, etc. And also, in addition to that, you could have data from our repository. There are over 2,000 data repositories in Rguroo's data repository, and for example, all of the R data sets and Rguroo and our packages data sets are here. And the nice thing about having a repository is that students can access data very easily. For example, here are the data sets that are in R, and for each data set you could just click on the information and you get some information about the data set. And to import it, you just say import, and as soon as you import it, then this data set becomes available in Rguroo, and then you can use it everywhere else in all other functions in Rguroo. Other things, of course, you can edit data. Then we have RGR files that are used for sharing your projects with other Rguroo users. So whatever you do in Rguroo is savable and it's reproducible. So you can save your work at any stage and come back to it. And also you can share it through RGR files. We have videos on all of these in case you need more information regarding how to use RGR files. You can see the videos on our website for these types of help. So we have also functions here under data, summary statistics. You can get various summary statistics for a data set, sort, subset, transform, if you would like to come up with new variables or transform your existing variables, etc., merge data sets and append data sets. Then in the section plots, you got bar plot, box plot, dot plot, histogram, pie chart, scatter plot, stem and leaf plot, and these result in very nice outputs, and they are highly customizable. And again, you could refer to some of our videos to learn more about them. By the way, note that at the bottom of each of these, there is like add folder, root, etc., and those are for organizing the objects that essentially you create within each of these functions. In the analytics section, we have proportion inference, which I will actually talk about both for one population and two populations. I will work with one population only today. We have mean inference, one population and two population. This is the new function, median inference, and this includes essentially non-parametric stuff like sign test or Wilcoxon rank sum test, and even some simulation-based non-parametric methods for median inference. Then we have linear regression, tabulation, goodness of fit. We have ANOVA, and then again, this non-parametric ANOVA is a new function that is coming up in our new version that will be released soon. And then you have analysis of contingency tables here. Then in the probability simulation, you have probability calculators for both continuous and discrete random variables. All of the random variables that are in R, you can actually, we have it on the menus for both of these continuous and discrete probability calculators. I will use this probability calculator today. We have random generator. This is just to generate random variables. And then this is multiple distribution generator. And this is a new random generator also that will be released in our new release, which will be hopefully will be released in about a month or less. The difference between random generator and multiple distribution generator is that in random generator, you are able to generate only from one random variable. In multiple distribution generator, you are able to generate from several random variables at the same time. Finally, random selection is to select randomly from a data set. And of course, this is useful, for example, if you want to do bootstrap or permutation tests, and you want to teach those types of concepts to students. We have videos throughout the software. Every dialog box that you open, there will be a video icon on it, and there will be videos for that particular function that you open. But at the same time, you could go into all of our videos and type in keywords, let's say confidence interval. If I just type in, then these are all the videos for confidence interval, and you simply just click on the video and the video will actually show up. I need to move this so I can close the video, and then you can just watch the video, a short video which tells you how to use the that particular function talks about that particular topic in this case. Here you see this icon, which is a book. This is our user's guide, and our user's guide is very detailed. It contains technical stuff as well as many examples that could be useful. So with that, let me just go back to my PowerPoint and talk about how you can use our Rguroo tools to teach proportion inference. So let me begin by reminding some of you guys might be familiar with Gay's recommendations, reminding you with some Gay's recommendations. So Gay's recommends teach statistical thinking, focus on conceptual understanding, and use technology to explore concept and analyze data. These are three main recommendations for introductory stats courses. And my goal here essentially is to introduce proportion inference with these recommendations in mind, and essentially say how Rguroo can be used so that we can heed these recommendations in our teaching. So let me just move to the next slide. And here, I just thought it would be a nice idea to do a quick comparison of classical methods and modern ways of teaching statistical inference. So the very first thing is that in the past, there was a lot of emphasis on central limit theorem, and mainly it was due to the limitations that we had because of computing. And in the more modern ways of teaching statistics, we de-emphasize central limit theorem. In the past, we used to have, plug in to the formulas and use a calculator to calculate things. Nowadays, we would like to let the computer do the computations and calculation and have students focus on concepts. I still see textbooks that have Z tables and T tables and so on. Those are the thing of a past. And of course, probability calculators are what we need to use. And in fact, perhaps avoid standardization is another topic that that I can talk about a lot, which can simplify our teaching. Finally, in the past, we used to work with theoretical sampling distributions, which had a lot of different assumptions, where now we can afford to use simulation-based methods or exact methods to reduce the number of assumptions that we need to talk about and give students. So with that, let's just talk about the proportion problem that I'm going to be talking about today. So at this stage of the game, I'm assuming that the students are familiar with parameters, and in particular now I'm dealing with the parameter P, which is the population proportion of success. And success can be any event, any specific event in trial of an experiment. And in order to make inference about P, what I need to do is I need to have some data, and the data is going to be the count of successes in independent trials. And remember that classically we use sample proportion, but I'm going to be using counts here. And at this stage also, the students are familiar with the binomial distribution, and so they should understand that these counts have a binomial distribution with parameters n being the sample size and p being the probability of success. So the problem therefore is to make inference about p using our observed counts of successes, of course. Throughout this webinar, what I'm going to do is I'm going to use this example. What proportion of CSUF students are Asian? CSUF is Cal State Fullerton, where I teach. And so on their website, they have the distribution of ethnicities as follows. So they have, CSUF has 43% Hispanic, 21% Asian, 19% white, 2% black, and 15% other, probably undeclared. And some of them are probably undeclared. And so the question is, are these percentages correct? So I pose a hypothetical here, and I'm going to say, based on my observation, let's say in number of Asian students that I had in my classes or something like that, I believe that the proportion of the students at Cal State Fullerton is more than 30%. Of course, this is anecdotal evidence, and I should clarify that with the student. So what we want to do is we want to really find out, let me just go back here and say, I want to find out whether my guess is correct or there is something wrong with the percentage, that 21% of Asians that is reported by the CSUF. So to begin this idea, I'm going to talk about sampling from Cal State Fullerton students. And so I'm going to take a sample of size n. We discussed how to take a random sample, etc. And then what we're going to do is we're going to count the number of Asian students in a sample of size n. And then I pose the following questions to the student. I say, suppose that I take a sample of size 25, and of course a random sample from Cal State Fullerton students. If in fact the true proportion of Asian students is 21%, how many Asian students would I expect or would I see in my sample? Would I see 4? Would I see 5? Would I see 8? Or all choices are possible? And a little discussion would go on here about the possible choices. And of course, the true answer here is D, all choices are possible. But then instead of giving them the answer, I'm just going to go and do a simulation in Rguroo. So let's begin with a simulation in Rguroo now. So I'm going to go and to the random number generator here. So I'm going to use the multiple distribution generator here. And what I want to do now is I want to go ahead and simulate counts. And we have already discussed that these counts have a binomial distribution. And I said that I'm going to take a sample of size 25, and CSUF had said that the proportion of Asians was 21%, so I'm going to put probability of success to be 0.21. Now rather than doing 10 samples, let's just take one sample here. And when I take my first sample, well, I took a sample of size 25 and I got 4 Asian students. Well, what if I take another sample? So here I have used seed 100. If I keep with the seed 100, I'm going to get the same random value all the time. So I'm going to just erase this seed and try a couple of times. So let's take another sample of size 25, and this time I got 8 students. If I just try again, it says you didn't change anything. I know I didn't change anything, but since there is no seed, it's going to give me another number. So this time 5, and so on. So they can see that, you know, every sample results in a different possibility here, right? Even 8 was a possibility that we looked at. Of course, notice that 20% of 25 is about 5, so 5 is an ideal value here probably. So let's look at 10 of these at the same time. So if I'm looking at 10 of these at the same time, I see that, you know, I have a sample of size 9, 6, 6, 7, 12, 8. And let me just actually go ahead and fix my seed so I don't get something different every time. So this time I just changed my seed. So I got 4, 4, 5, 2, etc. So each of these represents a possibility from a sample of size 25, right? And if we are going to estimate the proportion here, you know, we would get one of these samples. And what are the possible proportion estimates? Well, I can come here and again, I'm going to just take a sample of size 10. And for each of these samples, compute the proportion. Okay, so what I'm going to do is I'm going to just say add, and I'm going to say proportion. And in order to compute the proportion, I'm going to take, sorry, I need to click here. I need to take the value. The values are referred to as X, and I'm going to divide it by 25, right? So each value divided by 25 gives me the proportion of Asian students. So let me see. Sorry, I should delete. What is happening here? Sorry, let me just go ahead and create sample 2 here. Okay, there we go. Something is not quite right. Well, I know what's wrong. Sorry about that. I need to generate from a binomial. And number of trials is 25, probability of success is 0.21. That's what I didn't have. And I'm going to do a custom statistic here, which is my proportion, which is going to be x over 25. All right. I think I have done something with the sample one here. Okay, let me just get rid of this one here. Okay, I'm having a little bit of trouble with this. Let me just go ahead and redo this. Okay, let me add this. I'm going to go to do a binomial. And I'm going to do number of trials is 25. I'm going to take a probability of success is 0.21. And I'm going to do a custom statistic, which says it is going to be the proportion, which is x over 25. There we go. All right. Sorry, this was this is our test site, and for some reason I must have done something incorrectly in the previous one. Anyway, so the 21% now that actually I'm trying to estimate here is estimated by 16% by one sample, another 16% by another sample. This is not a bad one, the 20%, but then you can see that you get values as low as 8%. So with that, you can see that you can teach students that there is quite a bit of variability in sampling, and therefore what we need to do is we need to somehow account for that variability. Okay, so then, you know, we argue that there is a need for more than a point estimate. All right. So what can we do? We need to come up with confidence intervals or test of hypotheses, right? So let's begin with test of hypothesis here. So remember our problem here. Our problem is about the proportion of Asian students at Cal State Fullerton. And my guess was that at least 30% of the students are Asians. And we are going to do a scientific investigation, meaning that I'm going to just pick a random sample here. And the parameter of interest is proportion of Asian students at CSU. So if I am testing whether my guess is correct or not, then the research hypothesis, which is the alternative hypothesis, is that the P is bigger than 30%. And the null hypothesis is P equal to 0.3. And by the way, at this stage of the game, the students have already learned how to specify the null and alternative hypotheses. Okay. Now, let me go ahead and go and pose another question. So this one was about my guess. The other question was, could the CSUF's reporting be wrong? And remember that CSUF had reported that 21% of Asian students are, 21% of students are Asian. So the alternative hypothesis in this case is really two-sided, right? It is, P is different from 0.21. All right. So with that, I'm going to say, well, I took a sample of size 25. And again, another hypothetical. Suppose that in my sample, I observed 8 Asian students. Well, then I say, well, 8 out of 25 is 32%. It seems like my guess is really closer to the truth than the CSUF's 21%, right? But is this really right? Or is this just due to variability that we observed? Or is this by chance, in other words? Okay, so now we have to do a test of hypothesis. There are 2 approaches to testing hypothesis. One is based on critical region approach and one is based on p-value approach. And I'm going to do both. So for now, let's go to the critical region approach. What do I want to do? If we test at 5% significance level, I want to know for what values of the observed counts would I refute either the CSUF's reported proportion or my guess. So we're going to use the Rguroo's probability calculator. But remember, if I'm testing my guess has in the null p equals to 0.3. But if I'm testing CSUF's report, then the null hypothesis for that, to answer that question, is p equal to 0.21. And in both cases, the sample size is 25. So let's just go and find out what the rejection region would be. So let's go to the probability calculator here. And this is a discrete calculator that I need to use. Now remember, in this case, I want to give it some probabilities. I want my tail probabilities to be 5%, and I want to know for what values the tail probabilities are 5%. So for my example, or my suspicion, the trials is 25 and number of successes is 30%, right? And remember that the alternative hypothesis is p bigger than 0.3. Therefore, I want to see for what values the upper tail is. Let's say if I'm testing at 5% is 0.05, and I'm going to ask for a graph as well. So when I do this, I'm going to get the following. It's x binomial n 25 and p equals 0.3. And you can see that for x bigger than or equal to 11, the probability is bigger than 0.05, but for x bigger than or equal to 12, it becomes 0.044, which is less than or equal to 0.05. So I would reject the null hypothesis, and I would say my guess is correct if I would have observed 12 or more. I observed 8, so I cannot really say whether my guess was correct or incorrect here. So that is the rejection region that we obtained. Notice, by the way, that I cannot test exactly at 5% level because binomial distribution is a discrete random variable. Now, what about, let's just add one more. So let's call this one critical region. My guess. And I'm going to call this one critical region CSUF. And so for this one now, this is a two-sided test. As I said, the number of trials is 25, and the probability of successes is 0.21 in this case. By the way, notice that there are other discrete random variables here, but I'm just dealing with uniform here. And now this is two-sided. Because it's two-sided, I want the outside tails to add up to 5%. So I'm going to say lower tail 0.025 and upper tail 0.025 here. And I'm going to ask for a graph as well. So let's run this. So this was the first one, and now this is the CRCSUF here. And you can see, oh, sorry, I have to go back and do probability to value here, not value to probability. So I want the outside tails to be lower tail 0.025 and upper tail 0.025. Sorry, I did not check that. There we go. So here we have, you can see that if you choose x less than or equal to 2 and x bigger than or equal to 9, you're still above 5% level. But if you choose x less than or equal to 1 and x bigger than or equal to 10, you're below 5% level. So your critical region, therefore, is x less than or equal to 1 and x bigger than or equal to 10 if you're testing at 5%. And so here again, I observed 8. So interestingly, I cannot even say whether that the claim by the CSUF is incorrect. By the way, I have these pictures here for you guys, and I will share this PowerPoint with you. So the conclusion of the test is that there is not sufficient evidence at 5% level that my guess is correct or the university reporting is incorrect. So here we go into discussion of, well, what should we do? And we talk about sample sizes, and perhaps we need to talk to get a larger sample size, et cetera, et cetera. Now let's go through a p-value approach in computing, in testing hypothesis. So here I want to compute p-values. You have seen definitions of p-values in one way or the other. And so p-value, here is one definition. P-value is the probability that the test statistic X, in our case, the number of counts, is equal to the observed statistic, in my example, 8, or values that are more favorable to the alternative hypothesis than the X observed, given that the null hypothesis is true. And so X here again is the number of Asian students in a sample of size 25. So let's go ahead and go to, again, Rguroo and see how we can calculate these p-values. So let's add one more probability calculator here, and I'm going to say p-value, and I'm going to calculate p-value based on my guess. Okay. And here I'm actually computing probability, so it's values to probability. Before I was giving it probabilities and getting values, but now I'm going value to probability. So because I'm going to give it my observed value. So the number of trials is 25, and based on my guess, the null value of p is 0.30. And again, because the alternative hypothesis is p bigger than 0.30, I want to see what is the probability above what I have observed, which is 8. Okay. And actually, you can move things around. Let's just so I don't have to scroll down, I'm going to just bring this to the beginning so I can see the p-value as the first graph here. And let's just add the graph. Okay, so by the way, the rest are down here, but I just moved the one that I just did up here. This is probability calculation p-value for my guess. And you can see that probability that X is bigger than or equal to what I have observed is 0.4882. This is a pretty high p-value, which again is consistent with the critical region approach, and it says that you would not be rejecting the null hypothesis. Now, let's compute the p-value for the, let me just add one more. So let me call it p-value for the CSUF case. And let's just again move this a little bit at the beginning also. Okay, now to compute the p-value for two-sided test is a little bit trickier. So let me explain. So let's start with the number of trials, which is 25, and 0.21 was the claim of CSUF. Let me first calculate the probability of observing actually exactly 8 cases. So if I'm looking at that, so probability of exactly 8 is 0.07438. Now remember, what I'm looking for are cases that are less likely than 8 here in either large values of X or small values of X. So obviously 9, 10, 11, 12, 13 are less likely. They have a smaller probability. But on the left-hand side, 3 has higher probability, but 2 has lower probability than 8, as you can see. Okay. Therefore, in order to compute a two-sided p-value, I want to compute probability of X bigger than or equal to 8 or less than or equal to 2. So let's just go ahead and do that. So I'm going to say I want my outside to be, I want less than or equal to 2, and on the upper tail, I want bigger than or equal to 8. And when I just run that, then I get the p-value of 0.2153, which is the p-value for the for this test of hypothesis, again, not being able to reject, and it's consistent, reject the null hypothesis, and it's consistent with the critical region approach. So these are the ways to compute p-values here. Let me go back to the PowerPoint here. Again, I have these slides for you, which I will share after the webinar. So do the students have to go through all of this every time they want to compute a p-value or a critical region? Fortunately, the answer is no. There is a direct way to compute population proportion inference in Rguroo, and let's go and do these problems there. So let's go to analysis. In order to do things directly, go to analytics, choose analysis, and go to proportion inference, and we are doing one population proportion. Okay. All right, generally speaking here, if you had a data set, for example, let's say, you know, I had a CSUF survey and I chose sex and I you know, chose a variable, things actually automatically fill in. But right now I don't have a raw data, I have summary data, and so I need to actually input the data here. One of the things about Rguroo is that it forces the students to actually write, for example, what the factor is, what the success is, etc. And this is important because when the students read the problem, they should be able to, you know, figure out what these quantities are. And actually, when I do grading, I do grade them on these kind of things because they have to understand the problems in the context. So in our context, the factor is ethnicity, and a success is to observe Asian students. Okay. And for my sample size was 25 and the number of successes was 8 here, right? So as soon as I put that in, I want to do a binomial, not large sample Z. You see that the 32% showed up here. And now I want to test my hypothesis, which was that P is bigger than 0.3. Okay. So let's just run that. And now you get a complete report here. One population proportion inference, you get your data summary. It says there were 8 Asian students, 17 others, and there was a total of 25 students that were sampled. These are the percentages. Then you are testing hypothesis about ethnicity, and the method is binomial exact. So in this table, again, you get sample size, number of successes, sample proportion, and here is your p-value, 0.48815, okay, which we calculated earlier, by the way. This one is base factor bound. Unfortunately, I don't have time to talk about it today. This is based on an article that appeared in 2019 in American Statistician by Benjamin and Berger, and it's a very interesting index to look at. We do have information on that on our user's guide here, and you can look that up. And then you do get a one-sided confidence interval, which at this point of the webinar, I'm not talking about. I will talk about it later. And so you do also get a nice graph. And notice, by the way, that this graph is the same as this graph that we obtained here. It's pretty much the same. So essentially, I'm using calculators during my teaching, and for most part, students would use you know, this function to do their proportion inference, although I do give projects so that they can go through these probability calculations using the probability calculator. Okay, so what about critical region? Well, you can get critical region, and that's in the details part. If you go to the details and go to confidence interval and test of hypothesis and click on test of hypothesis, by the way, notice we have a lot of different types of methods here, but again, I'm not going over those in this particular webinar. So let's go to the test of hypothesis. And in addition to the p-value, ask for critical region graph. And then, of course, you can see that the critical region, it says the observed value is S8, critical region is X bigger than or equal to 12. And the exact significance level, remember, was 0.4425 that we had actually calculated in our critical region approach that we had, this value in the calculator here. All right, you could obviously do the same thing for two-sided tests if you're testing the claim of the CSUF, and you're going to get obviously consistent stuff like p-value is 0.2153. You're going to get the graphs that go with it, and so students can look at the graphs and understand what is going on with those. All right, so that is that. Now we come to confidence intervals using binomial exact. Unfortunately, confidence intervals are a little bit more difficult to explain at an introductory level when you want to use binomial exact. However, you can actually go ahead and you know, get confidence interval based on binomial exact, essentially just by going to Rguroo, one population proportion inference, the one that the graphical user interface that I showed you, or the dialog box that I showed you here, and you could just simply say, give me a binomial exact based on these confidence intervals based on this for whatever confidence level you want, and you do get confidence intervals. So maybe for the confidence interval, though, it might be useful to go into simulation type methods and use either large sample theory or simulation values to come up with confidence intervals. So in this case, what we are interested in, we want to come up with the distribution of the sample proportion p hat in a sample of size n, and we want to teach students what this sample proportion looks like, okay? So of course, in general, X is binomial n with probability of success 0.21 if you're testing, for example, the CSUF's claim. So let's go to the simulation function of Rguroo and see how we can teach this idea of sampling variability of the population proportion to students. So this time, let me just use the single random generator here. And also, I'm going to do something different. Instead of using binomial, I'm going to use Bernoulli. And the reason is that if I use Bernoulli, I'm hoping that the students understand this sampling process a little bit better. So I'm going to run this Bernoulli with 25%, with 21% probability of success. And let's just take a sample of size 10 here. All right, so you can see that in this sample, right, the first person that I observed was not Asian, the second was not Asian, etc., but the seventh person was Asian. So I got only 1 out of 25. Sorry, 1 out of 10 Asians, right? So this, you know, if I were to take another sample of, so let's just replicate, let's say 4 times. So these are, you know, 4 typical examples of samples of size 10, right? And you can see that, you know, this sample resulted only in 1 Asian student. This sample in 2, again, 1 Asian, but it was the second person that we looked at. Third one in 1, but then, you know, sample 4 has 1, 2, 3, 4 different Asian students, right? So there is sampling variability, and we want to know how it affects the sample proportion. If I want to compute the sample proportion here, you could, of course, go ahead and use the mean here. One other way is actually to just go ahead and, you know, say, I just say proportion here. I could say sum all the values, sum the ones and zeros, and divide by 10, right? And so you see, I got 10%, 10%, 10%, 40%. An alternative that I'm going to use here is actually, which leads to the same thing, and you might need a little bit of explanation to the students. If you take the mean of these values, also leads to the proportion, the same proportions here. Okay, so let's just use the mean here. All right, so I want to know what is the sampling variability of the sample proportion in a sample of size 10. I'm going to replicate, well, let's just take 20 of these first, okay? And run it. And let me just save this data set. By the way, you can save, you know, whatever you do here in your dialog boxes here, but then you can save also the values as a separate data set, as an independent data set. So let's save this data set as prop 10 because this was based on a sample of size 10. Okay. All right. Then what I'm going to do is let's just take a look at the graph. It's always helpful to look at graphs of these. So I'm going to just open a dot plot here. You could use different types of plots. I'm going to just use dot plot. And I'm going to use this prop 10, and I'm going to go ahead and plot these proportions. And now you can see that the proportions, there are actually 20 dots here, each one corresponding to one possible proportion that you get. And students can see that there could be quite a bit of variability. But in general, what does this distribution look like? And in order to see that, we can just go ahead and simulate a large number of times. So let's say that I replicate 1,000 times. Okay. So it takes a second to do 1,000 times. Let's just go ahead and call this prop 10A, for example. All right. And let's go back and look at the dot plot of this one. So let me just choose a different prop 10A, and I'm going to do mean, and I'm going to do this. And you see that actually the distribution is skewed to the right, and it is not quite normal. So, for example, the normal theory stuff is not going to work here. Also, if you think about it, n times p here is actually less than the usual rules of thumb, which says it should be 10, because n is, in this case, 10, and probability of success is 0.21, so it's about 2.1, which is a lot less than the usual 10 that we say is a rule of thumb. Okay, now let's increase the sample size to 100 and see what happens. Okay, so let's do that. Let's run it. Again, it takes a second. Notice that it has generated 1,000 values. Let's call this prop 100 and save it and go to the dot plot and do a prop 100 dot plot. And now here we see that, you know, the distribution looks normal, and now through this we can actually teach central limit theorem. I had an earlier webinar that I talked about these simulation-based methods in a lot more detail, and you're more than welcome to watch that particular webinar. All right, so let's go back to our own problem, which was the 25 sample size 25 case. So let's just go ahead and do sample of size 25 and look at the distribution of prop 25. Okay. All right. So now I have saved it. I can go here and graph prop 25. And that looks kind of normal as well. It's not too bad. It's kind of on the borderline, but I guess you could use the normal approximation in this case. And so how do we now use this information to come up with confidence interval? There are various ways to do this. One is to actually come up with the quantiles of this distribution. So there are 1,000 data points here. I look at the 0.025 quantile and the 0.975 quantile. And let me just go ahead and do that and see how we can come up with that. There's various ways to come up with these quantiles. One way to do it is just go ahead and sort our data. So let me just go ahead and take my data set, which is prop 25, and I'm going to sort it here. I'm going to say sort the means, descending. All right. So there are 1,000. So if I want the 0.025 percentile, I look at the 25th value, and the 25th value is 0.04. So that's the lower limit of the confidence interval. And if I want the upper limit of the confidence interval, I should look at the 975th value. Okay. So I can just do that in my case. And the upper one is 0.36. So my confidence interval is then from 0.04 to 0.36, right? There is also another way now that we can do this. So let me just go back to the PowerPoint here. So I have these again for you. Let me just go here for a second. So we could also talk about sample proportion plus or minus z times the standard error and compute the standard error using the our simulation method. And how do we do that? Well, if I just go over here and right click and say ask for data summary, then you see that you get the standard deviation here for this case, right? So the standard error for the 0.021 case is 0.082151, and then you have also the sample proportion. You could do sample proportion plus or minus z times the standard error. And in fact, if I just go back to the previous slides here, this is what we usually calculate in our, this is the true value of the standard error, but then the standard deviation that we calculated by the simulation is sitting here, which I saw based on the summary statistic. And you can see that they are very close to each other. And similarly, if you were to try the other case, you see that the standard deviation and the theoretical standard errors are pretty close here. Of course, you can also use the standard error using the sample proportion to come up with the standard error in order to compute the proportion. And to come up for the large sample Z case, we do have actually, you can go ahead and go to the proportion inference and select large sample Z, and you would get large sample Z results there. All right, I was just going to give you a quick view of how much difference it makes when you teach based on exact binomial versus large sample methods. The exact methods generally require, just knowing the knowledge of binomial, and then you can go on and compute p-values. Whereas the large sample methods here, you have to introduce the central limit theorem, the sampling distribution of p hat, and go through a whole bunch of computation to come up with the p-values here. As well as, of course, the fact that you need additional assumptions here, whereas you don't need assumptions here. All right, so let's go back here. So to end, at Rguroo, we provide one-on-one training and support for instructors. Also, we can give training workshops if there are a group of instructors that are interested in seeing more about Rguroo. As far as pricing, instructors can get immediate and complimentary access. There is no charge, and you can get access whether you adopt it for a class or not. For students, it is $20 for 12-month subscription. And finally, you can purchase Rguroo from Hawks through your bookstore. The ISBN information is here, or you can bundle it with any Hawks Learning product. Also, you can purchase Rguroo directly from Rguroo's website, www.rguroo.com. And if you want to purchase it through Hawks, there's a phone number here that you can use in order to order through Hawks. So with that, I just turn it back to Danny.
Okay, thank you so much, Dr. Jamshidian. I want to open it up to our audience for questions. So you can use the question and answer box. You'll find that in the top or bottom of your screen located on that panel. Just type it in there and I will read them off. At what point in your curriculum do you start with proportion inference?
So that's an interesting question. We actually start proportion inference right after we finish teaching probability distributions. In fact, we do proportion inference using binomial exact even before teaching sampling variability and sampling distributions. So pretty early on, students get exposed to the ideas of test of hypotheses and confidence intervals and all of that. So that is a very big advantage, in my opinion, of using the binomial exact rather than the large sample theory methods like the Z.
And do you cover the power of a test in your introductory courses?
No, not in our introductory courses. We do have an upper division GE course in statistics at Cal State Fullerton, and we do teach power in that course. But Rguroo does computations for power, for example, in proportion inference or mean inference or goodness of fit inference and all of that. So we do have computations in Rguroo, but we don't teach it in our introductory stats courses.
And how comfortable have you found your students with doing these simulations?
So we introduce a simulation pretty early on to students when we teach probability. we actually introduce simulation to them at that stage of the game. At the beginning, it does take a learning curve, and it does take them a little bit of time to understand. But by the time we get to statistical inference, they have done a few projects on simulations and so on, so they feel pretty comfortable overall, I would say.
Okay, we got one more here. Rguroo does not have simulation methods in your proportion inference function. Do you use the random generator, like what you showed, to do proportion inference?
Oh, yeah. So the reason that in the proportion inference we don't have simulation-based methods is because we have the binomial exact, which is always, which always leads to the correct answer, right? So that is why Rguroo does not have proportion inference based on simulation. And yes, in order to teach sampling variability of the sample proportion, we resort to the random generator. However, I guess if there is enough demand and we listen to our users, if you let us know that that is something that would be useful to have within the proportion inference function, then certainly it is possible to add it, because we do have simulation-based methods. For example, in goodness of fit, we have simulation-based methods. In ANOVA, we have simulation-based methods such as bootstrap or permutation tests in mean inference. So we have it everywhere else, but Rguroo doesn't have it in the proportion inference, mainly because there is the exact method, and the exact method leads to accurate results. And so perhaps that is the reason that we don't have the simulation-based methods there.
Okay, well, thank you again. It looks like we are just about out of time, but I appreciate you presenting this webinar today, and I would like to thank our audience for attending. If you do have more questions, you can direct those to us at marketing@hawkslearning.com, and we will get back to you. We'll be emailing everyone a link to view this webinar on demand, in addition to the PowerPoint slides and some of the other data generated here. So I hope everyone has a great rest of their day.
All right, thank you, Danny. And I should add that I will also generate the RGR files that you are going to be putting on the website, so faculty can actually replicate exactly what I did in this webinar.